Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and as we promised, we are going to talk about the linear momentum of a system, right? So this is going to be part 1 of our module series, and we'll continue it in a lengthy discussion of several modules. Okay, so linear momentum of a system. So what we have is, we are talking about the part 1 of our discussion. Okay, so the key concepts that we are going to touch upon in the next 2-3 modules will be that of the conservation of linear momentum, and the center of mass of the system. The conservation of the linear momentum and the center of mass of the system. And we have that the definition being, so what is the definition of the linear momentum? To begin with, we'll start very basic things to begin with, and then we'll increase the difficulty. So the linear momentum, so if a particle of mass m and velocity v, right? So these are the specifications. Then p being, which is equal to m times v, is the linear momentum of the particle. So we start talking about a particle, and then we slowly build the concept for a system of particles. Okay, so then the next natural question is, how about a multi-particle system? So for multi-particle system, we see that S being, so multi-particle system being P1, P2, Pn, right? And these are with masses m1, m2, mn, and we see that the velocities being v1, v2, vn, right? So these are the specification of the various particles in the system, and we see that the linear momentum, in this case the linear momentum of the system S, right? It's going to be of course the vector sum of the individual linear momentum of the particles. Okay, why the vector sum? Because we see that the linear momentum itself is a vector, because it has this velocity in its formula, velocity being a vector. Okay, so this statement says that if you want to talk about the linear momentum of the system, let's say PS, or sometimes I'll talk about the linear momentum being P of the system. I drop the convention S, P being summation mi times Vi, where I denotes the number of particles in the system, let's say finite n, and that is what we have, the vector sum, right? Okay, so then we will try to write this vector sum in a more convenient notation, so that the problem, when we try and solve these types of problems, it becomes easier to tackle with. So notice that let me write down. So what is this question is, suppose now the moment we are talking about a system of particles, so we have many particles and we are talking about concepts like linear momentum of a system of particles. We typically talk about we want to simplify the problem. We try again, go back from system of particle to again a point object or a single particle, and that single particle will be the center of mass of the system. So we try and simplify all the formulas to the center of mass of the system, right? So we have that. So we have what? So we have the linear momentum P can be written as m times v, right? Where v being the velocity of the center of mass, right? So v being the velocity of the center of mass, and we see what have we got? I need to define what is the center of mass. So we can define the center of mass as follows, the velocity of the center of mass as follows. So this is summation mi vi divided by summation mi, right? And of course this capital M is nothing but summation mi, right? Now when we plug in all these formulas, we are going to retrieve back the original formula, that capital P is summation mi vi, right? So capital M is the sum of all masses, and this capital V is the velocity of the center of mass, which is defined as I from 1 to n, which is defined as follows, right? Okay, so then what have we got? So let us proceed further. So we have started with the concept of linear momentum of a particle and that of a system, which is boiled down to the linear momentum of its center of mass. So now we can immediately write down the so-called linear momentum principle. So what exactly is this? Well, it is nothing but the conservation principle, right? So linear momentum principle. Okay. So suppose the problem says, suppose the statement, suppose S is acted upon by an external force Fi, right, and internal force. See, we want to make this setup as general as possible. So we talk about external as well as internal. So internal force Gi, right? And well, let me call it as Gij, because internal forces will be mutual among the particles, right? And the equation of motion for Pi is given by mi times dvi dt, right? And we see that this is going to be Fi plus summation Gij, right? And we see that this I is from 1 to, well, let us right now not include the summation over I. We are going to include the summation over j here, right? So now we are talking about the Newton's second law acting upon each individual particle's I, right? So then let us try and sum up this relation. So we have that, what is the total momentum of the system? Total momentum of the system is summation mi vi, right? And we can try and differentiate this total momentum of the system. So this is nothing but ddt of summation mi vi, and of course this is going to be summation mi ddt of vi, because of course mi's are constants, so it's only the velocities which are changing. So I from 1 to n, and we see that this is going to be summation I from 1 to n summation fi plus well, let me keep the whole summation fi plus summation over j gij, right? Okay. So so this is what we have. Well, I need to put the indices correctly here. J will lie, the summation over j will be from 1 to I minus 1, so that we can avoid over counting of the mutual interaction. Okay, so then what have we got? We can of course distribute this outer summation, and let us see what have we got here. So we can, well, I need to put in one more step in between so that the summation becomes slightly more clear. So the step is that this is going to be gij plus gji, and what exactly is this? We are adding up all the possible mutual interactions, and hence the summation is j from 1 to I minus 1, right? And then we can use Newton's third law. The third law says that gij is equal to minus of gji. Every action has an equal and opposite reaction for the internal forces, for the internal interactions, right? And we see that from this statement, we can see that the second summation is going to cancel out, and we see that dp dt, which is the total momentum of, or rate of change of momentum of the system, is coming out to be summation I from 1 to n times fi, where fi are the external forces, right? So what is this? This is nothing but the system version of the Newton's second law. That is the rate of change of the linear momentum, or the total impulse of the system is the summation of the external forces fi's, right? Okay, so then what have we got? So we see that this is what we have. Well, have we found out everything? So let us resubstitute. What is this P? So P is summation I from 1 to n mi times dvi dt, right? And then we can rewrite that this is nothing but summation, well, this is, we can rewrite this as, remember this summation is over the entire quantity, so this is going to be summation I mi times summation, well, we can pull out this summation of mi's and we can redivide this as mi's. So this is going to be summation mi summation dvi, well, too many summations here, summations over dvi dt. Okay, so this is what we have, and we can write down that this is nothing but the total mass of the system, capital M, and this is nothing but, this whole quantity is nothing but the total acceleration of the, well, total acceleration of the center of mass of the system, right? And then we boil down to nothing but the Newton's second law, which is acting upon the center of mass of the system of particles. Okay, so that is what we have. So we call this entire setup as the center of mass equation, right? So the center of mass equation, okay, the center of mass equation for the system of particles. Now individually the particles can do some individual motions. We are not going into those intricate details, but this is the general motion of the setup of the system of particles here. Okay, so then Let us this is so far a reasonably simple concept. We can look at this problem, this concept with a simple problem. Try to understand this. Okay, so what have we got? So the problem is we have a cat which leaps off a table and lands on the floor, right? So the cat is leaping off the table and it lands on the floor, and we have to show that while the cat is in the air, its center of mass moves on a parabolic path. Okay, well, it could be cat or it could be any object, so the idea is the problem is very general, and very little information is given in the problem, and it is asking us to show the trajectory of the motion of the object, and essentially we have to show that this is a parabolic path. Okay, so now the object, in this case the cat, is leaping, so the only force or the only external force which is acting on the cat is due to that of its weight, right? So due to gravity. So we see that again, why the object being cat? Because it is a complicated system of particle. We can treat the cat as a complicated system of particle. So we are not worried about that when the cat leaps, what happens to its hands or what happens to its legs and so on. The various internal arrangements are ignored, and we treat the entire object as a single particle. So we only are interested about the center of mass of the cat, and hence we look at the center of mass equation of the system of particles, which is the cat, right? So the center of mass equation, the CM equation, is d2r dt2. This is r being the position of the center of mass, right? The position of the center of mass. This is equal to minus g. Remember, this is as simple as this equation looks. We are talking about the Newton's second law applicable at the center of mass of the system, which is the cat. And we have written this second law in the form of its position, right? So we see that this is a second order differential equation. When we integrate twice, we see that the position vector r will be quadratic in time. Right, and that is exactly what we wanted to show, that the position follows a parabolic path, because parabolic being quadratic in time, right? So any quadratic equation, if we draw as a function of the independent variable, this being time, it's going to show that this is going to be quadratic. Going to be parabolic. So that's it. Okay, so then let us revisit the problem of cylinder rolling down the plane and see another version or another angle to this problem. So the problem is cylinder down the incline. We find the cylinder down the incline, and we find, okay, so we see that we consider a hollow cylinder, right, of mass m, which is rolling down an inclined plane, right? And from energy conservation, we can start to solve, the various aspects. We'll see. Again, we have already seen what is the acceleration of this hollow cylinder in one of the previous problems. So from energy conservation, the downward acceleration the downward acceleration of the cylinder is half g sine alpha, right? And we deduce the reaction force exerted by the plane on the cylinder. So that's the problem here. So let me write this and then we'll just revisit. So the problem says deduce the reaction force exerted by the plane on the cylinder. So that's the normal force we are talking about. Okay, so again what we have is the cylinder alpha, which is again rolling down the plane. It's a rough plane, and the velocity of the cylinder being v, and of course the alpha being the mass of the cylinder is vertically downward, pointing downward, mg, and the geometry says that if this angle is alpha, the angle with the horizontal, we have this angle being also alpha, right? So because the other one is 90 minus alpha, so this being alpha, and we see that again we need to find the reaction force. The center of mass equation, let us look at the center of mass equation. That will be m times dv dt. It's going to be well, the cylinder is rolling down, so the geometry says that its energy is we need to write down the forces properly. So we have sine alpha. So what have we got? So if this angle is alpha, we see that we complete the triangle, and the force which is acting downward, its vertical component along this direction will be mg sine alpha, because this being alpha, this is the vertical here of this triangle, this particular triangle I am talking about, which is the right triangle. So we have mg sine alpha, and I think the direction of the arrow is wrong here. It has to be mg sine alpha along this direction, right? Because the arrow is downward. So this mg sine alpha is aiding the motion of the cylinder here. And of course, we are talking about the reaction force, which means we are talking about, since the cylinder is rolling on the rough surface, the reaction force will be exactly opposing the cylinder, some sort of a friction force. So we have the minus F, right? So then what we can do is, so this is my friction force, not the reaction force, sorry. So this is my friction force which is opposing the cylinder here. And then we can similarly write down, so this is along the x direction. So what is my x direction? My x direction is this direction, and my z direction is the perpendicular direction to the motion. So along the z direction, we see that this is going to be 0, which is n minus mg sine alpha, which is the following. Okay. So then, if this is mg sine alpha, this perpendicular will be mg cos alpha. So we have the mg cos alpha. So n being the reaction force which is up, and mg cos alpha will be the force, the component of the weight which is acting downward. So we see from here that the normal force is nothing but mg cos alpha, and that is what we wanted to find from the problem, deduce the reaction force. So this is a simple problem at the very best, and that is what the problem was asking. Okay, so now we can also look at another problem. We can revisit the problem of the ladder, the 2D problem, and see what more information we can gather. So problem of the sliding ladder. Sliding ladder. So we have a uniform ladder of length 2a is supported. It's supported by a floor and wall. Okay, as shown. Well, as shown means we draw the same diagram. Here is the wall and here is the floor, and the ladder is of course making an angle initially theta. At t equal to 0, theta was 60 degree, and as shown, right? And the ladder is released from rest. The ladder is released from rest with theta equal to 60 degrees, and we want to find from energy conservation. We want to find the angular velocity. The angular velocity theta dot was equal to 3g by 4a times 1 minus 2 cos theta. Where is this formula coming from? See, we found the energy conservation equation of the ladder, and if we differentiate that energy conservation equation, we are going to find the angular velocity, right? So that's as simple as that. Okay, so then the problem is we made a major assumption while finding the energy conservation laws and finding the angular velocity. The assumption was the ladder is always in contact with the wall. That may or may not happen, right? So provided the ladder maintains contact with the wall. Okay, so we need to deduce. The problem says deduce that the ladder maintains. Well, the ladder loses contact when theta is cos inverse 1 over 3. Okay, so we have to find at what angular value the ladder is starting to lose contact with the wall, or the problem involves when does the normal reaction of the wall ceases to exist, right? Okay, we'll see in more detail. We have, I think we are running out of time here. So let me try and push this the solution to this problem in our next module. So thank you so far for listening. Thank you very much.